Welcome to the exercise on stochastic loading. As an example for stochastic loading on civil engineering structures, we are looking at the wind load on a high-rise building. The experiment you are going to perform within this exercise will be done here at the closed-circuit wind tunnel at the Department of Civil Engineering. We use that wind tunnel for different purposes. We use this for general education in wind engineering. We also use this for research on wind load on structures. We also look on the wind comfort and wind conditions in urban areas. We use it as well for the design and for the development of specific experimental test setups. And we also use this to generate validation data, comparison data for simulations with computational fluid dynamics. But before we go into the exercise and the different steps of the exercise, we will have first a look at the wind tunnel and the different features and the entire layout of the experimental facility. To get an overview of the wind tunnel and its different elements, we have here a sketch which is showing the individual parts of the wind tunnel. And as I said before, we have a closed circulation wind tunnel, the fan which is propulsing, which is moving the air is here in the upper part, and the airflow circulating in this sense counterclockwise through the wind tunnel system is entering the lower part here at the settling chamber. So since we are interested in investigating the wind load on civil engineering structures, on buildings, we need to have a flow which represents the main properties of the wind as it occurs in nature at reduced scale. Civil engineering structures like building or others are generally, if we talk about wind tunnel tests, investigated at reduced scales, which means everything which is relating to the wind loads has to be at the same scale as the model itself. So the lower part of the wind tunnel is, in principle, for the experiment, the most important part. So this is the working part or the working section of the wind tunnel. This working section of the wind tunnel consists of three main elements. So the first is here directly at the entrance where the flow is entering our working part. And this is a settling chamber. The settling chamber is designed to take out all turbulence and all unevenness which is in the flow due to the rotation of the fan, but also of the remaining duct system, so that we have at the start a very uniform distributed flow across the flow cross-section, and we have it at very, very low turbulence. So and from this point on, after the airflow passes the settling chamber and is entering now here our the remaining part of the working section, we have a flow processing unit. So as the name already suggests, so this is now this is processing the airflow in a way that we create or that we form the airflow with the main characteristic of the wind at the required scale. To do that, we usually have some roughness elements here in the flow processing unit. They usually are combined with some type of turbulence generators. In this case, these are spires, some triangular shaped plates which are standing directly here at the entrance. And from there on, after they have already created the first vortices, the first turbulence, so we maintain the turbulence here with roughness elements, and again, depending on which terrain type we are going to investigate, or in which terrain type our building will be located. So we have to adjust this part here in the flow processing unit according to the terrain type we are looking at. So the last part of the working section is now the test section of the wind tunnel. So there we are placing the model. So there are all the measuring instruments to take out the wind load on the structure. This can be the overall force on a building or on a structural part. This can be as well the measurement of surface pressures or the velocity around a building. We can look at the flow pattern, we can make flow visualizations, and so on and so forth. All that happens here in the test section. Since we have a closed loop airflow, we can take out the test section as such and have a free jet stream, or we can have it partially open, which allows us to easier access the model and our experimental setup. There are different, let's say, advantages to the different setups, but since we do have a closed loop, so we can do here in principle everything what we want and still have the same amount of air leaving the flow processing unit as it is re-entering the flow for further recirculation. So here in the sketch, just to show it briefly, here we have now the flow properties from the creation of the flow. This is here the mean wind speed profile. So this is usually, or the wind is increasing in terms of mean velocity with height. And regarding the turbulence, we have the largest amount of turbulence down here at the floor or at the terrain surface, and the turbulence intensity is then decreasing with height. So, and how this is doing it, in which fashion and how fast, so this is again a question of which terrain type we are looking at. So this is the general setup, but now let's take a look at the individual elements you have to consider now for the exercise, and let's make the description following the airflow after it has entered here from our settling chamber into our working part, into the flow processing unit of the wind tunnel. Good. So now let's have a look how the airflow is processed and how the wind loads on the building are measured and how are they transferred to full scale. For that, I have drawn here on the blackboard the main three elements of the working part of the wind tunnel. We have here again the flow in our settling chamber, which is now, because of the grids and the guide plates which we have in here, is now smooth and it is uniformly distributed over the cross section. So then we have here the flow processing unit, and we have followed by that the test section with the instrumentation for the wind load. Okay, so after now the flow is now entering our flow processing unit, we have installed inside here these turbulence generators, these flat plates, which are of triangular shape and which are create already the first vortices we have here. So they have the first imprint on the flow. So, and these vortex generators, these spires, they are followed by a roughness field. And this roughness field now maintains, on the one hand, the turbulence we have created here, but it also generates constantly new, smaller turbulences depending on the size of the roughness blocks we are using. So, and all that creates now here a turbulent flow which has a very specific characteristic, which means we have smaller size vortices down here. And we have larger vortices in the higher part of the wind tunnel, but all that is scale. This all should represent the characteristics of the wind as it is in nature. So when the airflow is now leaving the flow processing unit, and we just make a measurement of the airflow at the outlet, so then we have, if we have now the mean wind speed, so we have a function or a profile of the average flow velocity, which will look like that. So, and this is the mean wind speed profile of the wind. So this would be u bar as a function of the height z, the mean wind speed profile. And on the other hand, we have the turbulence intensity, or the magnitude of the turbulence. And if I draw this to the other side, it will have a function similar to that, meaning that we have right at the surface, right at the bottom, the highest turbulence intensity. So, and this is decreasing with height. So, and this is IU, turbulence intensity of the longitudinal component, as well a function of height. So these are the first two main characteristics of the wind when we are modeling this here in the wind tunnel. And a third parameter is the size of the eddies. So, and if I just draw here, for example, just one vortex, so the length of this vortex, if this would be an average vortex, again, so I'm measuring this now here in the longitudinal component, So this would be a measure of the geometric size of our turbulent flow. So this is actually a main difference if we, for example, talk about wind tunnel testing in general. So in automotive or aeronautical engineering, you take all this turbulence out. There you would like to have very smooth flow. There you are looking at a body, a airplane, car, whatever, which is moving through air. So which means the turbulence, or there the wind tunnel do have or do make a lot of effort to take all the turbulence out. Since we consider it the other way around, here we have moving airflow, we have here the wind over a terrain, over rough terrain, over a landscape. So with that we need to represent this particular properties. Good. So this is now the flow as we have created it here in our flow processing unit. So now we come to the test section, and in the test section we have now here a turning table. So this is this plate, and this turntable can be rotated in order to adjust different wind directions, to investigate, of course, wind loading from all different angles. So, and usually in the center of the turntable we are placing a model, for example, something like that. So, and then by rotating it and by exposing it to the airflow we have now created, we can now look at, for example, in this case, the wind load on the roof or whatever we are interested in. So in our case, we are looking at a high-rise building, and we also place our model of the high-rise building right here in the center of our test section. So this would look like something like this. And since we are interested in the overall loading, so not the load distribution, for example, the pressure distribution, we are looking now at the overall loading on the building, and that we can measure with a force balance we are placing underneath our turntable. And this is this setup here. So, and this is mounted on a turning device, and if we rotate it now manually, we have it here. So then we can turn the model with the force balance, and with that the coordinate system of the force balance is following the building. But this requires that we have a stiff arm with which we connect now the force balance to the model. So this is the setup we are working with, and the signal which is coming out from the force balance, which is containing the information regarding the moments and the forces which are acting now here on our building. So this is taken out to our computer, and this is then treated by a analog to digital conversion system. This is our data acquisition system. Okay, so now let's have a closer look on the forces we are measuring. So in our case, we are interested in two load components. We are interested in the overall drag force with which the wind is now pushing our building downstream. So this would be the overall drag force. This would be here FD, the drag force. And we are also interested in the overturning moment of the building. So, and both are defined, both shall be expressed at the base of the building. Here we have now our base moment, the overturning moment. So these two forces, these two load components are now of our interest. So, and how is, are now of our interest. So I said before that the forces are measured by the force balance underneath the wind tunnel. So, and this force balance has its own coordinate system. So, and if I'm drawing now the forces which the balance is giving us, it is giving us here the corresponding drag force. And it is giving us here the moment with which now the wind load is acting on the building, but related to the force balance system. So, and to recalculate, to use the results we do get from the measuring system, we have to relate them back to our model coordinate system. So both forces are in principle the same. So which means the drag force we are getting out here from the force balance is the drag force which is acting on the building, and we can place it directly at the base of the building, but the moment is different. And the reason for it is that the wind load only acts up here, and it has, compared to the coordinate system of the force balance, of course, a larger arm. And for that, we have to consider the eccentricity, or the extra arm of the balance coordinate system. So if I'm calling this now E, eccentricity, so this extra arm between the force balance system and the model system, we have now to compensate, which means the base moment is smaller than the moment is indicated from our force balance, and we have to reduce the part which is because of the larger arm from our results. And this is in principle just the drag force times the arm. We have here the difference between the base of the building to the center of the balance coordinate system. So that we have to consider if we have to, let's say, to condition, or not to condition, but we have to clean the results from influence from the experimental setup. So, but if we have done that, we are now come to the two forces, to the two load components we're interested in, base moment and drag force. So what we do now with it? So there are now different things what we could use the base moment and the base drag for. And one thing what we could look at is where is the aerodynamic center, and what is that? So the aerodynamic center is a point on the model, on our structure, where we could say that we could place the drag force actually at this point, and it would give us exactly this result. It would give us the overall drag if we just assume we use only one force, not a force or pressure distribution. And it would also give us the same base moment. So, and this is for high-rise building very often. Here, this is now our overall force we are putting on. So, and if the arm of this force is of a certain size, then this would give us the base drag and the base moment just by placing the force at one particular point of the building. So, and this arm, or this height, where this force is now acting on our structure, so this could be called, this is the effective height, let's call it HE, with which we could simplify the entire load process just to a one-point loading. So this would make it easy, this makes it actually easy to treat the complex situation of the wind load of a high-rise building to a one-point system, or if we talk it, or transfer it into a dynamic problem, so that we could actually replace the entire system to a 1 degree of freedom system, which has one loading and which has then, of course, or which is exciting a particular vibration here in our case of the high-rise building, and we could make a dynamic analysis. Good, but anyway, so the Eurocode, if you are going to design or look for wind loads on a high-rise building, so you not usually start off with a wind tunnel test. So there you would consult literature, and most likely you go first to the Eurocode, which is describing wind loads on different types of structures, and definitely on a structure as we have, a very standard geometry. So and there the Eurocode is actually talking about this effective height, and this should be around, it's approximately 60% times the overall height of the building, if this here is the overall height of our building. So the first thing I would like you to do is to take now the base moment and the base drag and calculate the aerodynamic, so the height of the aerodynamic center. And this is done by, so you could do this by dividing the base moment with the base drag force. So this is somehow a check whether our load follows at least theory, and the location of 60% is, of course, due to here our boundary layer flow, that we have an increase of velocity with height, which means the higher we do get, the more or the stronger is the wind force on our building. And of course then all the aerodynamic comes into play, the flow around and over the building. But the 60% is actually a good estimate for the location of this aerodynamic center. So this is something we would like you to calculate based on our results. A very important aspect we have to discuss in this case is how can we use the forces we have measured in the wind tunnel experiment or pressure or the observation of flow, whatever, to situations in full scale. How can we use the results we have obtained from a wind tunnel test for structural design? So the prerequisite of usage or of usability of the results is that the entire flow situation we have here is similar to that what we have in nature. So we started off with that we say that the flow we have created here in the first part has or reflects the main characteristic of the wind in nature. So the next thing is that also the flow around the building is reflected or has the same shape as it has in nature. So inside the flow we have velocity, we have of course with the moving air we have inertia forces, we have pressure distributions, and we have all different type of forces. Now we have the force acting on our structure. All these different forces, in case of similarity, assume a certain ratio to each other. And that ratio has to be established in the experiment, in the simulation, to reflect the same ratio of forces to each other in nature. And this is what similarity between a simulation and the situation in nature actually means. So then how do we assure that we have similarity? Well, there's one way of doing it. We can consider flow parameters. We can use the specific ratio, for example, of friction forces and inertia forces, of pressure forces, and we can look at different combinations. So this is what these flow parameters are looking at. So we can require that these flow parameters are identical in the wind tunnel to those in nature. Well, another way of doing it is looking at how this force ratio is developing. So if we are now looking at the forces we have on the building, so this is what we get from our force balance, we have now to take a force which is inside our flow. So and for that we are using the force or the power, so to say, the strength the wind has related to our building. And for that we usually choose the wind speed of the free undisturbed wind. So of course the building is now disturbing the wind, it creates a flow field around. But we are saying let's take the airspeed at the top of the building. This airspeed here, if I'm writing now, this is the mean wind speed now at h here at the height of the building. So this airspeed can create, in theory, a pressure when we bring it to a complete standstill. If you convert the kinetic energy into a pressure, so then we can say, okay, this is the potential load, this force here at the height of the building can impose on a structure. So, and this pressure would be, so if we transfer it into a pressure Q, this would be 1/2 the air density times the velocity now at the height of the building square. So this is a corresponding pressure to the velocity. This is, so to say, the velocity pressure or stagnation pressure we could create by converting velocity into pressure. So now we have a pressure, and if we would like to convert this into a force, since we are talking about forces down here, so we could relate this pressure now as an example on the entire surface. This is just now let's say it's a reference. It's not how the pressure really is distributed, but it's just to have a conversion of pressure into force. So and in this case, we could say that the force we're measuring here, and I'm writing this up here, Fd, our drag force, and if we compare that to now our velocity pressure times the reference pressure of our building. This will be the frontal area. So now we have a force at top. Now we have here pressure times area, a force standing down here. And this is now giving us a force coefficient, or in this case here, the drag coefficient. This is the relation between the force on the building and a force inside the flow. So, and if this coefficient is constant with respect to the change of the velocity, if we now increase the velocity in the wind tunnel, so everything of course starts speeding up, all forces do get larger, but whether the ratio is the same. So this is the question, and if this is the case, so then we have a stable flow field, and then we also say, especially if we have sharp edge bodies, and this is what buildings mostly are, so then we have actually established a independence, an invariance of our force ratios here in our flow from the velocity. So, and this is a second step what you can do, so which means that you perform your test at different velocities. Yeah, so we have here now different velocities at height of the building, for example. So, and we draw here our drag coefficient. So at very low speeds in the wind tunnel, we might have a drag coefficient which is down here, but it will increase until it reaches a more or less constant level, and we could say that from this point on we have similarity and this part we should not use for our tests, because here we still have a dependency of velocity and of our force ratio, which means it is not fully established, it's not fully in equilibrium. This is a very standard procedure for wind tunnel testing to make sure that our flow, our test condition, is actually at a velocity range, at a certain, let's say, development of our flow field around, that it creates or that it ensures similarity. So now finally we have to look at how do we control the airflow in our wind tunnel. And for that we have here at the entrance of our airflow, where it comes from the settling chamber before it gets processed, we have a control instrument installed. This is a pitot tube. This is looking like that. This is a pitot tube. And it is a quite simple setup. It has two openings. It has an opening here on the side, and it has also an opening directly at the entrance, at the nose tip of the tube. So this is now placed here in the airflow. It is pointing towards the approaching wind. And in these two openings, it takes out, it reads the pressure in the flow. So we do have a background pressure here at the entrance. Let's say this is P0, which is at both openings, of course. So we have it here at the side, and we also have it here at the entrance. But here at the nose tip of the pitot tube, the velocity right here at this tip is brought to a complete standstill. It has a perfect stagnation point. And with that, the kinetic energy of the airflow is converted into pressure. So, and this is an additional component of the pressure now read here at the, or taken out by the pitot tube. And if we say we have here these two sides, so, and this is conventionally said with this is the positive side and this here is the negative side of the pitot tube. So we have these two pressures, and they are taken out to a differential pressure manometer. So, and what we do get out is, of course, the pressure difference, delta P, what we're interested in. And this is exactly, if we subtract the background pressure from the pressure we have here at the nose, this is exactly Q, the stagnation pressure, which in turn is 1/2, again, as we had before, air density times the velocity square, which leads to, if we are interested in the velocity, so that here our mean airspeed at this point is 2 times the differential pressure divided by the air density, and we take the square root off, and then we have the velocity in meter per second. If the air density is kilogram per cube meter, and the differential pressure is given in Pascal. So what you need for the exercise is the velocity at height of the building. So, and that can be calculated from a factor. So in principle, the entire curve is a factor curve related to the velocity at the entrance. And with that, we can always, if we look at here our outtake here at our control manometer, we can always say how fast is the wind going at different heights if we adjust the velocity at different levels, especially if we are doing here this experiment by varying the main wind speed. So with that you can take out, and then you have the velocity with which you normalize the force. The base force, the same thing can also be done for the moment. So this is in principle the same procedure, the same idea. So with that you have all the results you need, all the data to perform the exercise. Okay, this is it for this exercise, and we hope that you got something out of how a wind tunnel test works. But it also, apart from just the individual technical issues and the procedures which are applied here in this wind tunnel test, this exercise should also demonstrate that in order to find the loading on a civil engineering structure, two disciplines are working together here. The one is the finding for the load, which the structural engineer needs to design the supporting system of our building. And of course, that the shaping, which is then the architectural part, can be used to reduce the loading. And if both do work very well together, so you can find the optimal design of your structure, of your building, and a setup like that can easily be used very early on in the project design phase. So since shaping the building, in this case it's a foam model, can easily be adjusted, can easily be modified, and you directly get out here the load from the building, and you can just put it into a quick calculation program which gives you an estimation of the maximum vibration of the building, of the maximum soil pressure, and so on and so forth. So this is actually a very good design tool as well as it is an engineering tool for the analysis of the structure. I hope you get something out of it, and I hope you enjoyed it. So thank you very much for participation.